All right, let me make this nice and big. So I've asked you the last couple of assignments, so after Monday's lecture and after Wednesday's lecture both, I put in as a part of what I want you to do is to take a peek at section 4.1. Now, we're kind of jumping all over the place in terms of the beginning of the book, a little bit at the beginning of chapter 3, end of chapter 3, some of chapter 4. They all go together. Math does that. It all fits together. But I think that this diagram relates nicely to the one we were looking at, this animation relates nicely to the one we were looking at the start of class on Wednesday. You remember like the green and red and blue bars and looking at how changes in x affect changes in y and dx and dy. Those changes themselves are related specifically if you have a constant rate of change. Now this is just talking about a single varying quantity, something we're labeling x, and as it varies from smaller to larger, where we started at was, just x varies smoothly. We can partition the variable's domain into intervals of length delta x, and we can still let x vary smoothly. Maybe keep track of which interval it's in as opposed to just what its value is. That might be something different we can do. So let me pause this. Out of the way, maybe that place don't go away. So if you can see right now, the value of x is maybe a little bit larger than 2. And every so often, they're not just at the integer marks. Those blue tick marks through here in between. It looks like a little bit before 1, a little bit before 2, farther and farther before. So maybe like about 0.9 units apart or so. So at 0.9, 1.8, 2.7, looks like there are these subdivisions that we've made along the x-axis. And so what we said is we're going to call these delta x intervals. So we can have these sub-intervals, just talk about sections of this. And still within each of these sub-intervals, as x passes through, it just still goes through nice and smoothly as we go from left to right. Just because I draw extra lines doesn't mean something different has to happen. But the reason for these, in addition to stuff we're going to be talking about with constant rate of change later, if you remember, we talked about dx last time, talking about dx as small changes in x and small amounts of variation as x gets larger and larger. So if I look at this picture, I know x was increasing here. It's just past one of these little blue tick marks. So it's just into a new subinterval, this delta x width interval. And I can see dx is small right now. Or x has varied only a little bit into that interval, or the size of dx is small. So it went from dx is fairly large looking there, has a largish value, and then all of a sudden it resets and starts again. So I can think about these small changes in x. I might want to think about where x is currently, where it's located in terms of its value, so graphically where it's located on this axis here. But I can think about these small changes in x starting from wherever I want. In this case, it's kind of arbitrarily about every 0.9 units. I'm going to start keeping track of how much x has changed. Maybe this 0.9 seconds represents something in a context. But every so often I want to watch x expand from new set points as its value actually gets larger, but thinking, well, what happens when x is between 0.9 and 1.8? Well, it grows smoothly from 0.9 to 1.8, and then it just keeps going. And this dx in that interval, thinking about, well, if I'm just declaring these to be positions where I'm maybe thinking about every 0.9 seconds, I want to see what happens. Well, during that 0.9 seconds, this x changed by 0.9 and then we restarted. Now, this seems kind of silly because there's not a second variable maybe related to what we were talking about Wednesday. Let's see, this was in, 3.15. Or maybe it was 1.5 I was looking at. It's the same diagram. Oh, I will not use that one. Here we go. This is what we're looking at on Wednesday. So I can see x increasing smoothly And dx, we said dx was just these little bits of appended change at the end. That's the same as what we were just looking at. And then up at the top, this mdx is a way to explain dy when x and y are in a constant rate of change relationship. Mdx is the same as dy. So what does delta x have to do with any of this? This one I have x and dx, and then there's also some y stuff. But do you see where the delta x that we were just talking about, those small subintervals, how that's actually represented here? There's not a symbol, but there's something. Yeah. Yeah, those gray lines. If you can see, these gray lines are, well, they're slanted, so it's maybe hard to tell, but those gray lines are actually a fixed distance apart. So this amount of change measured left to right corresponds to this amount of change in a second variable, or as x passes through this next interval that we're in the middle of, this next section, as that dx builds up, then we have an amount of dy building up above. So it wasn't labeled here because that's a lot of information to deal with all at once, but those little gray lines are sort of separating out one interval's worth of growth or variation at a time, both at the bottom, and then it's mapped to where that's represented at the top. So we can see the relationship of these sizes here. But yeah, thinking about these chunks of completed change, they map up above, but also as it grows, wherever x currently is, as we grow through that current interval of that same length, we should expect an interval of y of the previous 1.6 times as much length to be formed while we're within one of these intervals. But that doesn't mean I have to stop and just have 1 unit or 0.9 units of x or whatever it might be at a time suddenly appear. We let x change through all of the real numbers, take on any value, not just every so often pick a value and add on bits at a time. You can see the bits that correspond to one another, the sections between the gray lines at the top and the bottom. But as a new section arises, we'll have a new section arise at the top. So it doesn't just have to do with the completed ones and they appear suddenly. As x increases, y increases also. So I just wanted to point that out, that delta x actually is seen in this just without introducing that other symbol. And we're going to be dealing with that quite a bit, especially after your first test. But in any case, delta x that we've run across, at the end of class on Wednesday, we talked about variables, parameters, and constants. So relative to this delta x and the diagrams we were just talking about, we had a dx and a delta x. What sort of thing is dx in that diagram? A variable, parameter, or constant? Is dx something that takes on, it's a letter notation taking on a value of a changing quantity? Is it a letter that stays constant within a situation? Or is it a value that's like universally known? What about delta x? Delta x, is that something that was changing? Was it something that was constant within a situation but could change later? Or was that something that's universally known? Yeah, neither of those are constants. These are these where you could like look up in a book, what's x? The first time I took algebra in 7th grade or something, I remember in the front of my notebook when we solved our first equation, I wrote down x was something. I was kind of under the conception that once you figured out what every variable was, you got to use it for the rest of your life. That there isn't a book where you can look up what is x, what is dx. You can look up what the speed of light is in a vacuum. You can look up what the square root of 3 is. Those are constants. So these dx and delta x are not quite the same thing. Otherwise, we just use one symbol, say, forget about it. And one isn't like bigger or smaller than the other all the time. They both could come in a variety of sizes, but one of them changes all the time, and the other one stays constant for a while until we decide to do a different problem and change it to have a different value. Which one stays constant within a situation here? The delta x, right? It was like that 0.9. We had intervals set up that were 0.9 apart. Now, 0.9 was arbitrary, or maybe it wasn't even 0.9, I was just guessing. but it was definitely some fixed width that wasn't changing as we watched the animation. So that delta x is a parameter representing the size of these intervals. And in a different problem or later in the animation, we could change it to something else. But while the x was progressing, delta x was not changing. It was just being that width that was kind of a marker to measure where x was. So that's the sort of idea of what's a parameter. We'll talk about some more examples in a second. But dx, on the other hand, as x increased, dx kept going from 0 to, well, the size of delta x, and then started back over 0 to delta x. So it kept growing and then disappearing and resetting and starting, but it kept growing from 0 to that interval width and then restarting over and over again. So you saw it like kind of going like this, so it was changing all the time, back and forth through the same values. That's allowed. But it was changing all the time as x changed. So dx in this situation is a variable. It changes values. It has a domain to it. If you can think of how to explain a domain, what are the set of values that something takes on, you're probably talking about a variable. Probably, I say, because, well, a parameter, you say, well, I would definitely want it to be 0 or bigger for that delta x size. But in a situation, it's not going to change. It's going to be one of those, and it's going to sit there. So in either case, though, keep in mind these variables and parameters are things that have a symbol to go with them, not just a concept. Like I don't want to say an interval is a parameter. If I name the length of that interval delta x, then delta x is the parameter. And so we're talking about how to describe the symbols we've been using. So here's a situation. Cylindrical enclosures, tanks, are used for raising fish. So I've got a big cylindrical something, raising fish in it. One particular enclosure has a depth of 5.4 feet and a radius of r feet. And it was being filled at a rate of 17.9 gallons per minute. Water evaporated, we're refilling it, whatever. So here's a whole bunch of concepts or symbols potentially related to this fish tank. Take a few minutes, maybe compare with a neighbor. Think about whether each of these items labeled 1 through 9 is a variable, a parameter, a constant, or none of the above. So think about those definitions. If something doesn't quite fit those definitions, it could be a none of the above. There are some none of the aboves here. I'm going to give you a few minutes, and then we're going to go through these together. And so some of these descriptions look awfully similar, but none of them are identical. So read carefully. so as kind of a starting point, you see, lists like this. This isn't a thing that people ask you to do on a job. Hey, which of these are parameters, variables, constants? I just want to make sure that you've got the vocabulary down so that when I use a word, you know what I'm talking about. If you're trying to describe something, you use the proper words to describe it. But taking a look at this, numbers, let's see, 1 and 7 and 8 all sort of have the same thing. They're kind of related. There's a capital V and there's a small v and there's a capital V with a subscript of n. But the descriptions are also kind of similar. Capital V, number 1, says the capacity of the tank in cubic feet. All right, number 7, lowercase v, the volume of the water in the tank in cubic feet. What's the difference between the capacity of the tank and the volume of the water in the tank, just as a, not particular to this situation, but what's the difference in those descriptions? Yeah?
The capacity is how much water can be filled, and the volume of water in the tank is how much water is actually used.
Right. So what I said, in case you didn't hear that, the capacity is how much water could be in it, like the full, if it was all the way filled, that's how much it can possibly altogether hold, whereas the volume of the water in the tank is just how much is currently there. So just thinking about those two, is number 1 a constant, a parameter, a variable, or none of the above? It's a constant. Can I look it up in a book? And no. Yeah, and I can't even calculate it because there's not quite enough information. So it's not a constant, but it isn't changing. So what is it? It's a parameter. Yeah, number 1 is a parameter. I've got a capital V standing for this capacity, which is one fixed number. I just don't happen to know what it is. What about number 7, the volume of the water in the tank in cubic feet? Is that a variable or is that a constant? It's a variable. Well, how does that compare with number 8, the volume of the water in the tank at noon today? Yeah, V sub n, that volume at noon, that's one particular value of the volume because that isn't varying. Today at noon is one point in time, so there can only be one amount of water in the tank. But number 7 doesn't specify at one time, and we know that it was being filled. So if the tank is being filled, and I just talk about the volume of water in the tank, that is changing until I stop filling it or until I point out one particular point in time. So number 7, and I'm going to put up the solutions to these all at once, but I just wanted to compare these 3 first. Number 7 here is describing the varying quantity, the varying amount of volume in the tank because it doesn't specify one point in time, and it isn't full. It's just the volume. Now, domain-wise, the volume of water in the tank is going to be within a certain restricted amount of values. What's the lowest it could be? 0. And the highest it could be? Capital V, number 1, right? Up to the capacity of the tank. So it doesn't have to be 0 through some number. The volume has a domain 0 through capital V, or lowercase v has a volume 0 through capital V, which looks like a crazy statement, but like, oh, that capital V is standing for a fixed maximum value of this volume of water, the capacity of the tank. Lowercase v is something that varies between 0 and that maximum. All right, so number 1 we said was a parameter. What about pi? Constant. That's the one you could look it up. All right, so that's a constant. What about number 3, the depth of the tank in feet? Let's see. It says the depth, it says up above is 5.4 feet. But what's the symbol we've got here for number 3? There isn't one, right? There's not a symbol. It's not a parameter, variable, constant. It's a concept that we know is equal to 5.4 if you're asking us for a definition or a value of it. But we're using these symbols and calling the symbols parameters or variables or constants. So pi is a symbol. It represents 3.1415, etc. The ratio between circumference and diameter of a circle. V is representing the capacity of the tank, capital V in number 1. But number 3 is just the description. It doesn't have a symbol to go with it. So that's a none of the above. So do you see any others of these that are none of the aboves? Oh, sorry, I have 2 number 4s. I don't know how that happened. 1, 2, 3, 4, 4, 5, 6, 7, 8, 9. All right. So, yeah, number 5 also isn't any of the above because it doesn't have a symbol. It's just a concept here. Number of fish in the tank. And what about number 9? The tank's filling rate in gallons per minute. Also no symbol, so it's not one of these. But 5.4. If I say 5.4, the depth of the tank in feet, as opposed to number 3, saying the depth of the tank in feet. 5.4 is a number whose value is, means whatever it means, but 5.4 is a fixed value. It's not a mystery symbol that can take on different values at different times. It is 5.4. What about number 4, R, the radius of the tank in feet? Yeah, that's a parameter. It'd be kind of a weird fish tank if the radius was varying. Notice that we use this symbol up above, and lots of times when you see a symbol, it's like, oh, there's a variable for the radius. It's not a variable because it's not varying. It's just it's a symbol for the radius, and the name for that symbol that represents an unvarying quantity, we'll call this a parameter. So, yep, number 4, the second number 4, is a parameter. What about number 5 we said is none of the above because there's no symbol there, so the number in the fish in the tank is probably varying. If I were to assign a letter to that definition, that letter would be called a variable. I mean, I'm raising fish, so they get born, I fish them out, whatever. So the number could be changing, but I don't have a symbol for it, so I don't get to call that a variable. I can call this a varying concept. What about number 6, the H, the height of the water in the tank in feet? Yeah, that's a variable. It's being filled at a rate of 17.9 gallons per minute. So if I'm putting water into a cylinder and the radius isn't getting larger as I do this, then the height must be changing. That's how filling a tank works. Number 7 and 8 we already talked about. Variable for the first one and parameter for the second. And number 9 doesn't have a symbol. It's just a description of something that is, actually a constant rate. But regardless, there's not a symbol for this, so I can't call it a parameter. If I said K is the tank's filling rate in gallons per minute, then K would be a parameter. I would actually know K's value, which is constant. Yeah.
So, I'm sorry, why is the first 4 a constant, not a parameter? Because couldn't in another problem the depth of the tank be 7 feet?
So number 3, if I put a symbol in front of that, like Q, the depth of the tank in feet, I would call that a parameter. But 5.4 isn't going to be a parameter because I could change the depth of the tank from question to question, but I can't change 5.4 from question to question. So if I had a symbol representing the depth of the tank, that symbol could take on a variety of values. But since I have a number, just 5.4, representing the value of the depth of the tank, that 5.4 is specific to, it's a specific one number, and 5.4 can't change. I can put in a different number instead of it, but yeah, 5.4 itself is a constant. All right, so thinking about the varying quantities here, I think I have something that says it. Yeah, so we talked about already the domain of, which one was it? Oh, the volume, number 7, lowercase v, the volume of water in the tank in cubic feet. The domain of that would extend from 0 through capital V, the maximum capacity. Yeah.
How come 5.4 is listed as a constant, but then the tank's filling rate isn't?
So 5.4 is a constant. Number 9, if I called it a symbol, or if I wrote the number 17.9 there. So if I wrote 17.9, the tank's filling rate in gallons per minute, that would be a constant. The tank's filling, so these things that don't have symbols, this number 3, 5, and 9 that don't have a symbol to go with them, the symbols are the things that we're labeling as constants, variables, parameters. There are varying quantities, there are constant quantities, there are quantities that stay constant within a situation, but the term variable, parameter, and constant, as in not an adjective constant, but the noun constant, refer to the symbol that you're using for it, as opposed to the sentence that describes it. Other things, does that clarify? It is a little bit confusing because constant can be used both ways. But yeah, the concept is not changed. The value of that isn't changing, but there's not a symbol assigned to it, so I don't call this a constant. I can say that the filling rate is constant. All right, so the domain of this volume of water in the tank in cubic feet, which we said was varying, the domain was 0 through capital V, the capacity of the tank, number 1. What about the values of number 6, H, the height of the water in the tank in feet? What would be the domain for that? Yeah, 0 through, all right, the depth of the tank, 0 through 5.4. So including both of those if you want to get specific. But yeah, when you're thinking about things that are varying, you should be able to at least, even if you don't know precisely what the allowed values are, you should be able to think of what's the lowest possible, what's the highest possible. That should be a thought process that at least makes sense, even if you don't know those highest and lowest values. You can think of them possibly existing, or that it can be as large as you want. But if I asked you, what's the domain for pi? Well, it's just that 3.14-ish number. That's all. It's not, it never changes. Oh, that means it never changes? That makes it a constant. If I were looking at this r, what's the domain of this r, this radius? Well, it's only one radius in this problem. Like, in general, a radius could be anything bigger than 0. But in this problem, it's not changing. It's not taking on all those values. It's got one of them. I just don't know what it is. But in this problem, it only has one. In a different problem, a different fish tank could have a different size. All right, so let's move on from this. I want to talk about functions and function notation. That can help us out a lot in trying to describe when we're talking about relationships between two varying quantities. Function notation gives us a succinct way to describe precisely what's related or describe one half of the relationship without necessarily knowing all the details of the other. So, thinking about situations where one thing changes and it causes another to change. Thinking about, and you've seen these words before, the distance the motorcycle travels from an intersection in miles is a function of the time elapsed since leaving the intersection, measured in minutes. So let's say that I call that relationship G. G isn't a variable that I'm graphing or anything. G is just the name of the relationship between the miles that the motorcycles traveled and the time that's passed, all relative to this being in the intersection. So if I look at this symbol, pretty sure you've seen things like this before. G, again, is not a variable, so this isn't multiplication. What does this mean? All right, so I've got a function, G, that relates time and distance. So what's the 8.3 here referring to, do you think? Yeah, time in minutes. So what about the whole thing then? If 8.3 is about the time in minutes, what's G of 8.3? The distance in miles. Do I know the value of that? Do I know how to find the value of that? No, but this says it. So in this expression here, this 8.3, if we say, oh yeah, 8.3, that means 8.3 minutes. But this expression here is telling us three things, really. So the G of 8.3, whole thing together, that's the value of what we call the dependent variable, the thing that was caused to happen by the other part, the part that's inside the parentheses. So just, if you want to think like order of operations, what comes first? Stuff inside the parentheses. What happens later? What we get as a result of that. So I knew the 8.3 first, and that caused G of 8.3 to happen. If you want to think of it like a procedure like that. But g of 8.3 would be a number of miles, and specifically it's a number of miles that we determine by using this relationship g, knowing that our independent value, the number of minutes, was 8.3 that had passed since the motorcycle left the intersection. So this tells us all of that. If I just had 8.3 sitting there by itself, that doesn't really have a whole lot of meaning, but by saying g of 8.3, I'm saying, oh, well, g of 8.3 is a number of miles. I don't know how to compute how many miles, but it expresses this number of miles. It tells us that we're talking about a number of miles, and it also tells us when these miles occurred, however many they may be. There's g of 8.3 miles that the motorcycles traveled when 8.3 minutes have passed since it was in the intersection. So just keep in mind that you don't have to be able to compute this for it to mean something. You can still describe what it means or write this to describe something without having a means of computation. That's perfectly fine. So what if I do have something that looks like this? This looks like something you've seen in a lot of algebra books. F of x equals 3x squared plus 8x minus 17. If I say f of 2, what does this mean? Plug 2 in? Well, you can if you want, but we could find a value for this, but whether or not we find a value of it, it still has a meaning. This time we have a means to compute if we want to, but this means an output value. We don't have a name for what that might be called. Maybe it's y, maybe it's something else, but a value of a dependent variable when we're using function f and the relationship f, and the independent variable has a value of 2. So this is some f of 2 means on its own this value of the dependent variable. You don't have to compute it for it to mean that. The point of this is you can use these sorts of symbols, especially useful if you have parameters as inputs as opposed to numbers, or if you don't have a function rule, you just have a described situation. If you don't know how to do how the computations specifically work, or you haven't worked out how that relationship works yet, but you just want to describe a relationship, this notation again gives us a way to describe that dependent variable value when 2 is the independent or the input value. So mystery function here. So suppose we have two quantities, y and p, and z is a function that relates them, capital Z. And we have a formula rule, a function definition. Z of y is defined as 3y squared plus 8y minus 17. And z is the function that relates p and y. Notice there's not a p in that any place. That's okay. It tells us that z is the name of the function that relates y and p in the description. So there's a bunch of terminology that goes along with functions, and some of this you've seen before. Some of it might sound like it's talking about the same thing, but it isn't quite. It's kind of like parameters, constants, and all those definitions. Sometimes they kind of seem similar, and just talking about being careful with the wording we use. Here's a whole bunch of words that go along with functions. And I just said the first one a moment ago. But if I ask, what's the function definition? Thinking about even like, the definition of a word. If I ask you to define parameter, you'd be looking for, let's see, flip through the book, flip through my notes, where do I have what a parameter is? So what's the function definition that we have here? That could be 3y squared plus 8y minus 17. If this was like, okay, so in the equivalent, I might want to say a little bit more than that. The equivalent of like homework you might have done in an earlier grade. Can you put that in a full sentence, please? This is like we're missing the subject and verb, and we just got the object of the sentence there. So Yeah, z of y equals. So if you want to define something, and you've maybe even talked about this in recitation, if you want to define a function, you write something like that whole expression up there. You write f of a equals, and then some expression with a. That way, when you use the symbol f later, GC knows that you're talking about, oh, the function that you mentioned earlier. You've defined it already. So that whole first expression there is the definition of the function that we see. There's one function defined, that whole z of y equals 3y squared plus 8y minus 17. Now, what's the dependent variable? Z of y is a way to express the dependent variable. What else can we use to express the dependent variable? There's two ways in this. That would be how we compute it. P. Yeah, z of y expresses the dependent variable, and p expresses the dependent variable. It says so up above. Two quantities are represented by y and p. P is a function of y. So p is the dependent variable name. In that f of x and the g of 8.3 that we talked about just before this, there wasn't a name for that dependent variable other than just using the function notation. Like f of x would be the dependent variable for any value of x. That would give me the dependent variable's value for any value, or the dependent variable's formula is given by f of x. So I've got function definition. Dependent variable is z of y or p. P. Sometimes you'll see things like p equals z of y or y equals f of x, things like that. That's defining, oh, here's the dependent variable's name. It's computed using, or its relationship is given by, and then the function notation. What's the independent variable? Y. Yeah, kind of like the y is what we start with. If you're going to start from someplace, it's the y. If you're computing something, here we have a computation available. You plug in a y and then you get something out. But you don't have to have a formula, again, in order for it to be the independent variable. It's just whatever the symbol is that's the inside part, or whatever is the basis of our relationship. That's the independent variable. What's the function name? Z. Yeah, z is the name of the function. What about the function rule? Yeah, that's just this right-hand side, really. Yeah, function definition and function rule. Don't get too hung up on the differences between those, but function definition, you need to have, like the complete sentence, how do you define this so that somebody else knows what you're talking about? You need the name, the symbol, equals something. For the function rule, that's really just the computation rule. What is the computation I'm doing? So that's really just talking about the right-hand side. In any case, what about the value of p? P is a variable, so it takes on a variety of values. It's okay if it's not just a number. But how would I find a value of p? Yeah, I can write z of y. I can write 3y squared plus 8y minus 17 for any y. Yeah, so the value of p it's not the same as z. Z is a function. P is the dependent variable, takes on a variety of values. Y is the independent value, takes on a variety of values. Independent variable, takes on a variety of values. Yeah, the value of p, I can say z of y, like we were talking about in the previous, like that g of 8.3 is a value of the dependent variable. F of 2 is a value of the dependent variable. Z of anything I want, and including z of y, it's not one value, it's all the values of the dependent variable, depending on, because y can vary. So z of y would then vary. All right, so let me skip out past these. And again, for this dependent variable, you could have p or you could have z of y, either one. So can I say something like z equals 3? No, z doesn't equal 3. Z is a relationship. So it doesn't have one value. It's the whole definition up there defines how z acts on any independent variable y. So if somebody wrote that, what do you think they might have meant? Yeah, maybe p equals 3. Or what else could you write? Z of y equals 3 for some value of y. I mean, z of y equals a formula, but z of something, like z of a equals 3 for some value of a. But yeah, z can't equal a number. Z is a function relationship. So in any case, they might have met p equals 3 or z of something equals 3 for a particular something. And I don't want to try to calculate out what something would make that true. But, all right. You're going to get a worksheet that has all of these on there. But here's a little practice at function notation. I'm going to start passing these out from the front. Your recitation TAs from the back. This is not an assignment to pass in. This is a, let's work on this for a little while, talk about it for a little while, and you're going to finish this up over the weekend. Yeah, so we've got about 10 minutes left. Finish this up over the weekend for continued discussion on Monday. But rather than having you have to copy all this down, I'm just going to leave it up there, but you'll get some copies yourself.
It's like, if you want to, these zeros need.
Yeah. Let me get over here, I'll come down that side. So you can see them up there, maybe a little small. And I think I made enough extra copies so that. All right. Remember when you get this, take a look, see what you can do with expressing things using this function notation, and then at the bottom you can see in number 3, the reverse, looking at already written function notation and trying to figure out how you would describe the meaning of that. Like we did with the g of 8.3, but more symbols. Who does not have a worksheet? Anybody? All right, you have spare copies. But I'll post this on Canvas. So if you want a fresh copy, you lose this between now and Monday, etc. You'll have it. So after a couple minutes, I want to go through number 1 and a hint on number 2. And see how much time we have left after that. But 1 should be a pretty quick one. Do it. Oops. All right, so number 1. D is a function of t, means that D is uniquely determined by the value of t. We're going to talk more about what it means for something to be a function on Monday. But just based on that and your previous knowledge, which of our variables is independent, or which quantity is independent? T. Yeah, so it's our time quantity. Is this going to write for me? Ooh, there we go. It's our time quantity, T, that's independent or determines the other, which the other variable symbol is D, distance. So the quantities are really talking about the amount of time and the amount of distance traveled, but variable-wise, just to say this briefly, T is the independent variable, D is the dependent variable. Using a function named W, write an expression for the distance traveled, D, after any number of seconds, T. So how would I write that? Just define this function, not a rule with computations, but just using the symbols. W of T, yeah, so W of T, W is the name of the function with an independent variable T as the input. And this is equivalent to the dependent variable. So I could write D equals W of T. I don't have a calculation rule for this, but this defines how these quantities are related. W is the function that relates independent T to dependent D. Now, in terms of number 2, and this will also help with number 3, so that you can get a good chunk of this correct over the weekend. If I want to know how far the car traveled in the first 9 seconds it was moving, those first 9 seconds it was moving would be what values of T? Between 0 and 9. All right, so just thinking about the interval that we're involved with, this is time 0 through time 9. I'm just writing it as interval notation. So this is talking about between time 0 and time 9, how far did the car travel? Well, how can I find the variation in distance during that time interval? Yeah, W of 9 and W of 0 are going to be my distances traveled at those 2 points in time, so I can subtract those. Now, there's another way we could do this also that's slightly shorter in this one particular case, but it won't work in the others on here. What's the value of D of 0? It's 0, because it's defined as distance traveled since it started moving, and if it's been moving for 0 seconds, it hasn't traveled anywhere yet. So you could just write this as D of 9. But thinking about 2B and C and D, other sorts of intervals, what interval is...
Jennifer, you mean W of 9 and W of 0?
Oh, yeah. Yes, I do. Thank you. Sorry. If I do that, please yell at me. I don't want to confuse you. So apologize. Yes, I do mean W. W is the name of the function. D is the dependent variable. Yeah, so our W value at 9, the value of the function at 9, and the value of the function W at time 0. Which this would be some distance, this is some other distance, and we can subtract final minus initial to get the distance traveled, or the change or variation in distance during that interval. So if 9 seconds have passed, this is completed change. You read that whole description maybe on change versus variation. If this is done, we're done. So the distance traveled by the car between t equals 2 and t equals 9 seconds, not too much different, right? Just W of, it's not the interval 0 through 9, it's 2 through 9. Right? So just think about, and so we're about out of time for the day, these intervals between t equals 2 and t equals 9, that's the interval 2 through 9. If I want to know what distance was traveled during those, I need to know the dependent variables at the beginning and end, final minus initial, to get that change during the interval, or the variation that happens as we pass through it. All right, so work on the rest of these. Parts C and D are a little bit trickier, but similar to this.